This is the time to start. Okay, so today we're going to do the second session of this. I want to start with the lab experiments to demonstrate the. Can you please close my door on my office? Okay, so we are going to discuss a little bit about any experiments that you can come up with to demonstrate the loss of electricity and basically the loss of electricity, and it's quite simple, right? We have only two. We have Ampere's law and Faraday's law. Any other law can be derived from them or manipulation of them. Like Kirchhoff's laws, you can do it by manipulating any one of them. So let's see what some basic equations we have. We already saw a little bit about Ohm's law, for example. Ohm's law, we know exactly that the current is the voltage times resistance, but it's more general than that. It's a function of time is equal to the voltage, a function of time. Resistance is a function of time. So even if we have a resistor that changes, for example, right? We have, I don't know, this would be the value of the resistor with time. Even we have a resistor that at some point has discontinuities, the law will still apply. How will we get resistive values? Well, just put some switches, right? We just put switches. It's not too complicated. We have maybe a linear resistor and maybe some other resistors that switch on and off. But frequently, what I find in when teaching even my graduate classes is that students don't believe that Ohm's law applies with time, and this is, of course, the relation between J and E. All right, so how do we demonstrate that this works, or how do we demonstrate that it works for an inductor and a capacitor, or a series of inductors or capacitors? Normally, we'll include building a circuit of some sort, maybe some function of time as the source, and measuring the voltage at the terminals and the current at the terminal. Let's call it what we would call the PCC, the point of common coupling, which is what differentiates the source from the load. And this is very idealic. It's an ideal behavior of these things, but it will work. If you go to the lab, the devices, inductors, capacitors, etc., work very close to this. Well, there are some parasitics, there will be some resistance, some other things, but it will work very well. So Ohm's law, there will be no problem. So you can have a source and you will go that. What about, how do you demonstrate that the voltage in an inductor is a function of time, is LDI is a function of time, dt? Can anybody give me an experiment in which I can change that? And this is related to Faraday's law, if you wish, right? How would you verify that this equation is correct? And we are going to circuits. We are not even getting into electromagnetic fields. So how would anybody will tell me, oh, I want a set of experiments in which I'm sure this is going to happen? Well, you need to build a circuit like this, right? and apply a source. So you build your circuit with some source, you have an inductor, and you have a way to capture the current, but not only the current values, RMS or peak or whatever, but you actually put an oscilloscope and are able to see, to capture these things in the screen, and you're able to see figures. So if you see, obviously, if you have, this is your voltage, and you have a current that will be behind because it's an inductor, you're going to have the current like this, right? I mean, you see it sinusoidal, will be fine. Hello, you came a bit late. So this is going like a class. You can stay or you could whatever. You are not a prisoner. All right. Okay. So, but if you want to demonstrate that equation, this is not enough. This is just a little case, right? So you say that the voltage is ahead of the current because it's sinusoidal. It's not very convincing. Scientifically speaking, it's like saying, well, I do a test, and if it works, let's say I throw stone into a lake, and because I can kill a duck or something, I'm gonna kill it every time, right? No. So one way to do is just to change the source, right? Let's change the source. So the voltage source, instead of being a sinusoidal, let's make the voltage source a square wave. Even give it a little bit of things like that. Okay, so if I make this, what the current will be? If it is true that this law holds, how would the current be? Because let's assume that this is switching. So I will start with the current at 0, and the current will rise in this way until it gets to that point. And at that point, it will go to 0. So it will try to go down. And when it gets to this point, it will still go down with a different slope, right? Let me change the slopes here a bit. It's going to be like this. No, it's the other way around. This slope is larger and this one is smaller, and it will go like that. And then I can repeat this thing, right? And if I have a current that looks like this, when the voltage looks like that, I have, well, okay, it is following the relationship. And then I can change lots of shapes. So I can start with, of course, sinusoidal. I can have a impulse. I can have, I don't know, square waves. I can have sawtooth. So sawtooth. Well, it's not giving me the red. So I can have all these excitation voltage. And if the current or the relationship between them for a sufficient number of cases holds true, so if I hold that this is di dt dt, and this is correct for, I don't know, how many you like, how many experiments you think will be enough? 5, 10, 10 million? How many? 10 million, right? So do you think people have experimented with this in the different labs of all the universities in the world, and high schools of the world? Have they experimented and done it like this? I think at this point, there is sufficient evidence to assure that this happens. Now, the challenge is the other way around. The challenge today will be, can you demonstrate that it is not true? There has been so many experiments, so many people trying to do it, that the real thing is, where does this doesn't hold? Well, what if your inductor is nonlinear? What if I have a nonlinear inductor? when you have a nonlinear inductor, this equation is a simplified version, right? The actual thing, the actual thing would be curl of E. And I don't even want to use that. Curl of E will be equals minus d dt of B, right? That is a more general way of writing this. Yeah. But of course, I am not going to go all the way to that. But from here to here, there is a big step because one is general macroscopic, the other, it's still macroscopic, but it's to a point. All right. And I am going to avoid the use of the nabla vector as much as I can. Just call it the curl. So, and the divergence also will be this. I'm not going to use this thing. I'm going to try to use just divergence. Not always can, but I will try to. So like this is you have to put lab experiments to demonstrate each one of the laws of electricity. Ampere's law and Faraday's law being the most important ones. The circuit equivalent is something like that. All right. And that's all I'm going to do regarding experiments. But make sure that every one of those laws can be demonstrated with an experiment. If you really want to have the feeling that Maxwell equations are correct, you need to have experiments for all of them. Okay, that takes me directly to Maxwell equations. Maxwell equations are experimental. And as I said, you need to have, today, you will have to create an experiment that shows that they are not accurate, they don't meet, they are not solid. If you don't have an experiment, we would just take them as true. And an experiment that makes them fail. Of course, they'll fail at the microscopic level. But the good thing about engineering, not physicists, is that we only care about the macroscopic world. Yeah. Do I care if the electrons and protons are fighting with each other? No, no. What I care is how much money I can make out of a material, right? That's what we engineers care. We go by the money. Remember from the previous session, here is the money. This is the money, right? Both of these things, E and H, are these things are the force. Force times distance is energy, and nobody will spend energy if you don't get paid. So this is the money. Okay, so let's say what this is saying. This equation is telling me, forget about the magnetic field intensity. It's just a force, magnetic force. Call it magnetic force. Don't call it magnetic field intensity because you are already trying to confuse yourself. It's a force. Let's talk about money. It's a force times distance. So through magnetic forces are produced every time that we have some current. This crazy thing, this is simply the current. That's what it is. It was the current in a conductor. We can say current in a conductor. And this thing, well, the whole thing here, this is the current in a dielectric. Yeah. This part is due to a dipoles, plus minus, applied to a source. And they will not circulate unless there is a change with time. The dipoles, you can charge them, a capacitor is charged, and that's it, current is finished. But the current cannot really go, the electrons cannot go from one point to another. But this is more like if you go to a movie, they used to see those lights moving around. That's what is happening. The current, the electrons are not escaping. The electrons are just like a fictitious way of seeing they move. All right, so So the Maxwell equations in the integral way, which is really the one that tells you the story, um, cannot be solved for a general geometry. Those integrals here are relatively difficult to do. This integral is difficult to do unless you have very nice geometry. And only three geometries you can solve. It's either a sphere, a cylinder, or a cube, or some rectangular prism. So if you don't have anything like this, for example, you can very easily solve, you can very easily solve the Maxwell equations from a part of a sphere or a cylinder that is charged, as we will see in a moment. Here, my friend Fayaz is going to illustrate some beautiful figures. So you could see this right away for a cylinder, but it could be a sphere too, and it's the same thing. And you can do it only for these three geometries. But if I tell you the field for electrostatic field for a figure like this, and this is a charged thing with a positive charge, can you tell me, can you give me an expression for the electric field outside? Probably you can't. Yeah, of course, engineers, especially smart engineers from the 1900s or even earlier, would say, oh, well, I can kind of draw it, right? I can kind of see how it is. This electric field is going to be perpendicular to this, assuming that this is a metal. And then I can even draw some deformations, and then you go through the complicated thing of conformal mapping. But you would not be able to really get a number, right? You can get pretty this. Before we had final elements for applied to electrostatic or electromagnetics, I designed my machines in the 1980s with conformal mapping and with deformations, a lot of eraser and pencil, and it worked very well. But it wasn't so precise. But it was sufficient for the engineering precision that was needed at that time. But today we want to do things better and better and better and better, so we have to do better things. And running final elements today takes, as you will see, running a case like this, it would take, preparing the case probably takes 2 minutes to an experienced final element modeler. And the solution is probably obtained in 10 seconds because you need to do a little bit more clickings. But you can solve a problem like that once it is built in no time. All right, so let's look at what this Maxwell equation is saying. Let me see. I am going to take the first one. Let me use the same area that I put there. Area J dot dA, blah, blah, blah. Lots of vectors plus partial derivative with respect to time of the area integral of d dot dA, right? So what this is telling you is that the force field around some path is equals to the current that is enclosed. So this is, let's say, the magnetic field intensity which is, of course, given in amperes by meter, right? But remember, this is the force. So the magnetic field intensity is equals to the current enclosed, which is current enclosed. But both currents, conduction current and displacement current. If you were to put a circuit, what this is telling you is somehow you have a circuit, you have a conductor that is carrying current, and this conductor is going through a capacitor, if you wish, and somehow the current needs to close in itself. Current going one way doesn't exist. It has to return somewhere, right? We already know that. It's like you cannot create water out of nothing. Water needs to circulate. So current is just like water. It's a fluid that cannot be a well, somebody will say, what if I have hydrogen and oxygen and mix it and I get one? Yeah. Anyways, so there is always one way to complicate my life. But running water starts on some place, ends on other place, and it always goes from the high point to the low point, which means this is like this: high point positive, the low point. So, and you can only have current circulating if you have current circulating here. Your magnetic field will be lines like that. And if you don't have alternating current, the current will stop. If you have alternating current, then there will be dipoles here changing sign, and then the current can go back and forth, back and forth. Now, if you don't have a capacitor and you don't have this term, then it's all right. You can simply do it with conduction current. So let's say, just for a illustration, I'm going to leave the illustrations of Fayaz later. I need about 10 minutes around 2 p.m. I have an interview of a candidate for a position here, so I have to go and see. Only 10, 15 minutes, but Fayaz will entertain you. We have already, so what Fayaz is going to show you is a conductor that is carrying current this way, and is going to show you the vectors. I want only the vectors, outside and inside. So if you have that, you will see the arrows. The more you see this as vectors of force, and also the size, the length of them will be longer and longer as you go in and smaller as you go out. The more you visualize this as vectors, the closer you are to see that this is really money, right? So I know we are used to see equipotentials. We are used to see equipotentials, mappings, colors, surface plots, but and even streamlines. Yeah, we are used to all those things. But the real way is look at the vectors. If you look at the vectors, it will never tell you a fault. So what this is telling you? This is telling you that around a conductor that is carrying current, there is a force field. And the force is trying to push you to circulate around the conductor, right? So you've seen the experiment that you come with a compass, right? You bring your compass. Let me put an orange compass. You come with a compass, right? And it has the north and south pole, and it will align with those lines. So, all right. So this is the first equation. Yes, ask the question.
Figure you draw forward. Yeah, here. Oh, no, this is the circuit one. So, what's the difference between the conductive current and the
Displacement current?
Yeah, displacement. But if they are in series, then they are.
Oh, no, it's the same value, but you will also have a magnetic field here. Let me put the magnetic field in red. You will also have a magnetic field around this. Okay.
Yeah.
But the magnetic field there, let's say that only that part exists. It will have to be changing with time, otherwise the current stops.
if there is a movement of charge, then there is a current.
If there is exactly, if there is a movement of charge, there is an electric current, and there is a magnetic field produced by that. Yeah, that's simple is the circumstance. Yeah, and how do you know? There are those called Hall effect meters, right? So Hall effect sensors. So they can feel the magnetic field in there. The magnetic field, the force that the magnetic field produces. So let's be very clear. We're talking about force. We are not talking the abstraction of magnetic field intensity. That doesn't give me money. What gives me money is the force. So I need to go and look and chase the money. Oh, unless you have some spiritual, I don't know, purposes. But we're engineers. We're here to make money. I don't know you. You want to make money, right? Yeah, exactly. Yeah. So if in the meantime, if you have developed new theories on the way to making money, well, all right. So I am not going to discuss more of the equations because I want to get to how to make the money. And not only that, I want to say, let's make the money and let's quantify the money. So for that, as you have seen, Maxwell equations are full of integrals. And they are full of integrals. Let's say these things, contour integrals. There are the surface integrals. There are the closed surface integrals. And there are volume integrals. So, so we have integrals. I have put there the book by Shea. I think Shea is the best description I've seen on the interpretation of these things. But let's start with the work integral. We already discussed a little bit about that. So we say work integral is force times distance. And this is given in joules or in dollars. Depends on how you measure it. Okay. Now, this is for high school. In university, we learn how to integral. So we take f dot dl is basically the same, but it is a vector. Now, this formula assumes that the force and the movement are in the same direction, right? That's why there is no other thing. But in the contour integral, the things cannot necessarily be straight, right? You can have a force field that is going this way, but maybe there are things in between. Maybe you have an obstacle here. Maybe you have an obstacle there that doesn't allow you to go straight this way, but you will have to go around and around and around. But still, the force that matters is given by that dot product, is the component of your movement that is against the force. If you go transversal, you will not you will not gain any energy or do anything. There may be situations, I'm talking right now about electrostatic fields. Electrostatic field will only depend on the amount of distance that you move from one point to another. But because that's what we call a conservative field. But we have a non-conservative field. For example, what about here? I can just, let's say that this is not a magnetic field force. Let's say this is a whirlpool in a lake or in a river. I can travel for free if I am here, right? I locate myself here, right? I am here. And just jump into a little chalup, canoe, whatever you want to call it. Just jump into it and travel here for free. And you have moved there for free, right? Now, only humans go against the current. So instead of nothing in physics is against the current except humans. So if you look at electric current goes from the easiest path, but we humans don't always follow the easiest path. We sometimes just take the hardest route just for fun, or because we don't know better. But so on this way, you will have already traveled for free the distance from here to here if you were planning to go that way. But there will be somebody who wants to go against, and then it's going to work twice as much as needed. So those fields, the fields that make you rotate, are non-conservative. So those are the core fields. All right. But let's go back to this. So we can tell right away that force times distance is either I have to pay money to move, or somebody has to pay me to move things. There's no way out. Okay, so in the first two Maxwell equations, these two Ampere's law and Faraday's law, here we're talking money, right? Both of those need to do with money. Either I spend it or I receive it. Now, let's look at the second or the right-hand side terms. And this one has only one hand side term. And this is the quantity. So this is the money, basically how much you pay, and the quantity is how much you get, right? So that is what the flux integral is measured. Flux integral, let me put it here, but flux integral is exactly giving to you a quantity. So say you are putting this force in here and you want to know how many cows have you been able to put into in a corral, right? So here you have your cows, right? How many cows were you able to move into some place? So for that, we use the flux integral. Flux integral are surface integrals, right? So for example, this area, let's say, I'm going to put J dot dA, right? This is a surface. This is a quantity. For example, I don't need to count the people inside this room to know how many people came in, right? So at this point, we have 2, 4, 6, 7 people we are here. But it's enough for me to put a counter at the door and see how many people cross through the wall, through the door, to know how many people were inside. If I know there was nobody inside before, I start counting the people coming to the door. I don't need to come here and count the arms and legs and then divide by 4, right? I can just count one by one as they come through the door. So flux integral gives you the quantity, and we normally do the surface integral for this. So, which is here, right? We say the amount of something that is crossing, an area or a surface, I can do it by integrating this surface, right? Because maybe some people went below, some of them went out, but if I cover all that, it's the quantity. So Maxwell equation, right? Like you say that H dot dl equals to the surface integral of J dot dA, right? So what this is telling me is the money that I put resulted in so many, in this case, amperes, or the other way around. How many amperes I have, and that will give me how much force I can get. It's a reversible equation. Yeah, I can go from one way to the other and from the other to the way. It's an equal sign. It's not a diode. It's an equal sign. It's a conductor. things can go in and back, right? All right, so we are measuring now the quantity. This other element over here, right? It really doesn't matter much because it's only a change of time, but the integral is the same. This is mostly the charge, right? The d dot dA is the charge. So, okay. There is one more integral. There's one more integral that is important to know, which is the volume integral. Volume integral, well, is the measure of how much stuff is in there. Normally used for the sources, not normally used to account for the effect, but it's normally used for the sources. What is the volume integral? Well, the volume integral is, well, now we don't know how many people came through the door. We were here too late, but we can come inside the room and start counting the people point by point, and it will have to be the same. So at some point, you say the volume integral is total quantity. Not only how many of that quantity or how much of that quantity cross through the door, but the total already there. Maybe we are counting people in there, but there were already 10 people inside the room. So if we came in late because, I don't know, the subway was running slow, and people already got in before I started counting, I need to go inside and account for everything inside. So I need to do a volume integral. Of course, the volume integral will be a cube. We have to use the cube. We can use the sphere, we can use whatever, but the cube is the easiest thing. I don't know you, but I am an engineer. Have you ever tried to design your house? No, I have tried. And the basic element of design is always the cube. That's why you need to hire an architect. Okay. If you're going to build your house, hire an architect, because if you design it, or we engineers design it, it's just going to be cubes. Okay. Right. So no curves, no spheres, nothing. It just, that's the element that we use. And try to think about any problem. The first thing you do on any problem that has to be with distance, all right, a Cartesian coordinate system, and I need to know where the north is and where is the east, and then we're talking. Hey, we're trained this way. So we are not saying, oh, what if we invent a system with curves like that, which is more aesthetically pleasing, right? No, we don't use curves or crazy things. We use a cube, right? Okay, now there is a very clear relationship between volume and a volume integral and a surface integral. Right? You can count. So if you do the volume integral of whatever quantity, let me put a vector f, or not a vector f, but a quantity. Let me see, what would be good? Charge density, dV. Yeah, charge density makes a good example. So inside this cube, there could be a uniform distribution of charge. So let's say, let me actually put a little bit of these things. So there could be charges distributed one way or another, charges and charges. It could be that they are distributed uniformly. They will be distributed uniformly if what I have inside is a dielectric. If I have a dielectric material and it's uniform, how do we call it? Homogeneous, isotropic, and linear. If that happens, we will have a very nice distribution of charges. Remember, charges are like people. They don't want to be next to each other. It's the example of the subway. The first person picks a place. The second person goes as far as possible from the first person. And as they keep on coming, they try to be as far as possible from the next. Of course, there is a point where it's just so full that everything is packed, but it's kind of uniformly distributed, because if you see a little space over there, you will go through there and move and try to make the distribution of people uniform. So the same charges would do, but they would do it much better than us, because they will know, they will sense the force and will say, hey, wait a minute, I'm feeling too much force here, and I am not happy if I have to spend energy. I am happy when I can sit, relax, and that. So only humans don't distribute perfectly uniform, but charges in a material with distribute uniformly. Now, how these dust charges got in? So I have a volume with uniform distribution. How is these charges got in there? Through the surface, right? There is no other way. They need to go to the surface. So this would be equals to the closed integral of a some quantity. Let me call it the force or the quantity. The charge, the area, right? It cannot be charge. It has to be charge density. Surface charge density dA, right? The charge will be a volumetric distribution times volume. It will also be surface distribution times surface, and the abstraction that doesn't really exist, which is the linear distribution times distance or distance. This will be times area. And we use these crazy things like a linear distribution of charge. There is no such a thing as a linear distribution of charge. A linear distribution of charge means that it has no volume, which means it doesn't exist. Everything needs to have a volume. Now, it is a very good mathematical tool when I am, for example, trying to compute the field coming from a conductor. A conductor seen from the distance, it will look like a filament, right? So it really doesn't matter. The engineering error that I'm going to make by estimating that conductor as a linear distribution of as a filament instead of something with volume, it doesn't matter. It's much less than a few percent. And we remember, we are capable of accepting 5% easily, maybe even 10% error, and no problem with 1, 2, 3% error. You just forget it. It's not even worth discussing that point. All right. So if you want to do it in the integral way, you will say the charge will be the volume integral of the volumetric distribution of charges, and it will also be the surface integral of the surface distribution, and it will be the linear integral of the contour integral, the linear distribution dot the here you have point dot dl. These things need to have some direction. So I can measure the amount of charge if I am able to consider all the flux that came in there, all the charges that went in there from the beginning, assume that it was discharged, then I have no problem doing this. Okay, so these three concepts are very important. You have to say, over here on these equations, the money we can sell, this is the force. Okay. And this side is the return on investment. Okay, so you put this much force and you get that much quantity. Or you put this much quantity and you get certain amount of force. It's reversible, as we said before. All right. So any questions to this point? No questions? Yes.
How do you define the direction of the volume?
The direction, no, you don't find it. You put the volume any way you want. Things are not there. Things don't exist there. You put them in a way that makes your calculations easy. For example, say that you want to see what is the quantity of a flux. You have a flux that is going like that, right? Produced who knows how. So if you want to compute the quantity, you will come here with a surface that is perpendicular to that, because you don't want to do integration, right? You don't want to do, you're going to put a rectangular surface. You're not going to put the surface like that, right? Because it's going to complicate your integration life, right? You don't want to integrate to this, right? You want to integrate to something. In fact, you don't even want to integrate. You just want to multiply the quantity by the area. Yeah. So you try to always put your integration path in a way that is following the force. Yeah. Now, that is very important if you're trying to do things analytically. But we are not trying to do things analytically. We're going to do them here through finite elements. So we really don't care. We really don't care. We just, the program can do point by point by point by point. So, all right. Okay, now I have a challenge. I have a challenge for you. Everybody needs to think a little bit. And the way to think is with what you know, contour integrals will give you force, flux integrals that give you quantity, and volume integrals that give you quantity. Now, say now that in this room, something is being produced. Yeah, I know. At this moment, nothing is being produced here. We are not creating any product of any type. But let's say that you want to design a mathematical tool based on what we learned that allows you to measure the quantity of something, call it fluid, force, whatever, is being produced at a point. So, at a point, we can say in the room, totally in the room, but let's reduce it to a point right here in the center, right? So, for me, to be able to solve Maxwell equations, the integral way of Maxwell equations cannot be solved for a general problem. There are some integral equations, some people try to do conformal mapping integration of solving these very complex integrals, and they get some degree of success, provided that everything is linear and nice, because easy integration can only be done on a linear system. Yeah, you can always take a derivative of whatever. I can give you a crazy function, a really, really crazy function. Yeah, let me give you a crazy function. For example, e to the x by gamma multiplied by the sine of omega x, and all this to the power of 1 minus x. And if you want more complicated, I can add 3x, right? I can take the derivative of this, no problem. If somebody tells me, take the derivative with respect to x of that, it will gonna take a few pages, but I can do it. Can you take the integral of that? No. You need to immediately switch to a numerical method. You need to do something. You need to plot this thing. Some wild people, but smart, will say, oh, this is the function of the plot. and now I'm going to get the area under that, right? And it's a pretty good thing. And that's what people would do, right? But some integrations are very difficult to do. Derivatives are not. So what I'm trying to do is I am not going to solve Maxwell equations in the integral form. I need to pass them into a derivation form because I can always solve differential equations, always, right? I cannot solve integral equations. They don't even teach them it at school any longer. I don't know if you ever took an integral equation class, but probably you didn't. And why not? Because they are not very practical. Theoretically speaking, they give you a lot of things. I mean, in electromagnetics, we have the green functions and all these things that are great, but very limited in what they can do. What they do well. But if you want to really solve Maxwell equations for whatever, you need to go in a differentiate in a derivative way. All right, so that's your challenge. Tell me, with what you know, I want you to design a mathematical tool to measure the quantity of a particular product generated at a point. The easiest thing is, okay, let's take a point in the middle of a cube and say it's producing electric field or something, right? Quantity of something. So what will you do? Yes?
Is it a gradient?
Gradient? No, no. The only thing I know so far is to take integrals. I haven't been able to do anything else yet. Just take the integrals. Find the area. But the area is not going to give me what is inside.
Find how much force is going to each side.
It's already there. It's already there. So how much quantity went into the thing? That would be fine, right? Say, if the total quantity in was 0, there is nothing inside. But if the total quantity is different than 0, something went in there, right? So I need to do a surface integral of each surface, right? I need to get this surface and this surface and that surface and that one and that one, right? I have 6 in a cube. And remember, I am an engineer. The easiest thing for me is to take a cube. You can take a sphere if you want. And the integration will be easier. But in the end, the final equation in spherical coordinates or cylindrical coordinates will just drive you crazy. So we just stick with Cartesian coordinates forever. So I need to account for the total flux that went in there. That's what Carlos said. I agree with Carlos, right? So how much is the total flux that goes in there? Well, whatever quantity, closed integral of the quantity I'm going to represent by F dot dA. And I need to do this integral for the 6 faces of the cube, right? This is for the 6 faces of the cube. Okay, but that is not telling me on a point. This is only telling me on a big cube, right? If I want to get it into a cube, I need to make the limit smaller, right? So that I get so that I don't need to say concentrate into a little volume, I'm going to say what is the volume. I'm going to divide by the volume that this equation that this integral is given. And if I want to get to a point, I will have to compute the limit when the volume tends to 0 of this thing, right? And the thing is that it's not only the volume going to zero, because I can flatten the two surfaces and the volume is to zero. All dimensions need to go to zero. So delta x tends to zero, delta y tends to zero, and delta z tends to zero. And this is to represent the fact that delta area tends to zero. And this equation has a name. This is called the divergence of f, right? That's the name that it has. The divergence of f, which is given by a surface integral on all six faces, reduced to nothing. It will give me the amount of something that is produced at a point. If this quantity, if this divergence, which I will call divergence of f, if divergence of f is greater than zero, it means here that flux is being produced. If it is equals to zero, it means that flux is not being produced there, but there could be flux. Flux could be there. Just the only thing is that I am not producing the flux at that point. It can just pass through it. And if the divergence is smaller than zero, it means that the flux is consumed. Something in there is a monster that is eating flux, right? It's either I have a source, it's being created out of something, the flux, and this, there is nothing I can say. There is nothing I can tell whether or not there is flux. The only thing is I say the flux is not being produced there. But I cannot assure that there is no flux when the divergence of a particular quantity is equal to zero. I am going to have to go at this point. I am going to pass the control to Fayaz. Fayaz, for those, is Fayaz. That's his name. Fayaz is here, a PhD student who has done a lot of finite elements, and is going to show two examples. He's going to show if the field of a charge that is in a cylinder, and is also going to show the case where current is coming out of this, and he has prepared. He's not going to go slowly on teaching you how to use the program. He's just going to use it the way he says. He's going to describe the clicks that he does so that you could potentially reproduce it if you have it. Tell me, in Mexico, you have access to a program, a finite elements program now.
Yes, I have access to console, doctor.
Very good, because we're
Francisco.
going to use console. So everything that is Fayaz is going to do is in console. We also have here ANSYS, but we have somehow decided that console is our tool, but we have used ANSYS. So we can share the files. I don't know which version you have. Sometimes there is conversions with things, but Fayaz is going to illustrate the figures that I want you to see. I only want you to see lines, flux. I only the lines of force, and I am going to go out for a moment. So I'm going to make you the present. You let me. Stop my presentation. Let me stop. How do I stop here? Stop share. And now you have to share, Fayad. Here you have. No, not me. Maybe student's account, but not professor account. Okay?
Okay.
All right. see you in 10, 15 minutes. It's very important that I meet this candidate.
Okay. Okay, good day. My name is Fayaz Ali Jandan, and today I will
Speak louder, please.
okay, so I will show you the examples Professor just mentioned. So I will go with the easy way. Since this is the very first class, or I consider it as an introductory class. So I will try to make the geometry the very, very easy way and try to simulate the these things in an easy way. So often when you will click this console icon, this window will appear. So sometimes this type of window appears. So the easy way is just I click this model wizard, and professor wants to show these examples in 2D. So I will go in 2D. Just click this 2D. And the first example through which I would like to start off is the
Hold on, please, I cannot hear you.
okay.
Yep.
So let me see. Okay. So there is a physics AC/DC. In this AC/DC, there is a electric fields and currents. So we will go with electrostatics, since we have to model this one charge, and we have to see the electric potential as well as electric field. So that's why we have to go this into electrostatics. Just double click it, and this option will appear over here, and then click the study, and then the types of the study appears. So with this very first example, as I mentioned that we are going very easy, so we will start with stationary, right? So just double click the stationary, and then it will start. This type of interface will appear, and the easy way. So the first step for doing the simulation is to create a geometry. So we have a lot of efficient ways to create a geometry, but I'm doing the easy way. So just go to this sketch option. Okay. So in the sketch option, there is a circle. So just click the circle and go into its center and just click and then like move outwards. So let's suppose just leave it over here. So this is our circle, right? So right now I'm not taking care of this size and shape. Sorry, the numbers related to the size and shape, but just a sketch. After that, we need to create another circle that is this way, a bigger one. So, and after that, just click the geometry and then hit the sketch, and this geometry is ready now. So this is a very easy way to create the geometry, and here I have not taken care of the numbers, the dimensions, and that thing. So if you want to change the dimensions now, then you can easily do it like click the circle one and change the radius and the sector angle if you want to, and the position as well. So this is the geometry here. Okay, one thing to mention here, that the software automatically selects the dimensions in meters. So if you want to change the dimensions, just click the geometry, and here's the option length unit. Change it to millimeters if you want to. Right? So you can change the unit length over here. Or else, if it is in meters, then you just have to just click, write it this way and mention the units here, right? So since it is already selected in millimeters from the geometry, now there is no need to add the units. So the geometry is there. Now the next step is to select the materials, right? So for the materials, just click the material, and this type of window appears over here. So in the material, we need copper as well as air. So for this, there is option built-in, right? So in the built-in, there is option air. Just double click it, and it will appear over here. And after that, copper. Okay, so these two options will appear over here. So when you will click this air, this software automatically selects these two domains. So, but since we want this domain to be air and this to be the copper, so we're just removing this thing and selecting it separately. And the copper, that's the copper, right? So we have selected the materials now. So after that, we need to select the boundary conditions. And for that, we have to click the electrostatics here. So in this electrostatics study, so you can see the number of options are there. So here we just have to right click it, and here there is an option of a terminal. So for the terminal, you have to select this terminal. So we have now selected the boundary conditions for our conductor. So there are many ways to select the boundaries. So in this, if you right click it, there is like a terminal option there. You can also go with electric potential there, right? So this is the boundary selected for this conductor. So now to select the boundary for this outer space. Okay, so again, right click it and go to the ground. And for this ground, we want this boundary to be at 0 volt, right? So this is there. So the terminal, so you have an option. Either you want to put charges on it or you want to put the voltage. Let's suppose if we want to go with the charges, so we can say that it is 1 coulomb, right? So after that, the next option is meshing. And in the mesh, the easy way is to select the mesh, the physics control mesh. Else you can also customize your mesh as per your geometry or complexity of the geometry and the computational power you have. But for now, we are just going with the easy way. So just click the physics control mesh, and over here the element size. So before going to this element size, just click the build all. The software will automatically create this and divide this whole spaces into the small sections, and the software will apply the partial differential equations and solve this thing. But okay, so for accuracy, you need to increase the size, and let's suppose if we are going with extra fine, then you can see that this meshing increases, right? So as we go with increase in mesh size, or then the accuracy will be more, right? So just build on and then go to the study. After that, we just have to click the compute, and it will take a few seconds. And then here you can see the electric potential, right? So in this electric potential, the software has already found this electric potential here and the electric field norm, right? So the electric field norm tells you the intensity or the magnitude, and you can see that electric field intensity goes low as it goes from as you are approaching the boundary, right? So if you want to see the if you don't want to see these lines, so you can just hit this, right click this streamlines and disable it. Here is that, right? So in the same way, if you want to see the electric equipotential contours, then just go to this over, right click this and click the contour. Then you can see plot, and you can see the equipotential contours. So if you want to see it like more clear, just disable the surface. Now this you can see these equipotential contours more clearly. Clear? So any question to now?
Can you bring the curves back, the field curve?
The electric fields?
Yep.
Okay, so if you want to see the electric fields, wait. Okay, so you want to see this thing, the same thing back?
Yeah.
Okay, so just enable this. So this is the electric potential, right?
Yeah.
So this is the electric potential that is changing as you are moving away from the conductor. So you can see that in the conductor, the electric field is 0.
Yep.
And it increases as you are moving away from it.
Yeah.
So
I mean the lines that you highlighted at first.
okay, so these are the electric field lines. You can see the expression over here. Just plot it, and these are the electric field lines.
Yeah. So inside the copper,
Yeah.
why it looks like
Yeah. So I asked the same question, Professor. Professor says that it is just because of the meshing. Okay, so it's not considerable. And we know that the electric field inside the conductor is 0. So I have tried with the different boundary condition, like the terminal, this one, this terminal I try and selected it as a domain, And in this, they were not there,
Oh.
right? You can try this terminal. That's why I mentioned these options here.
Oh.
That you also have this terminal boundary condition, and it will just like take this whole conductor as a domain, right? So here, like you might have seen that when I was selecting this terminal, I was selecting the boundaries, right?
Yeah.
Okay, so with this option, you just have to click this just like as a domain, as a conductor, right? So you can try with this as a
Okay.
domain, right? So then you will not see these lines inside that.
Okay.
But as a matter of fact, that electric field inside a solid conductor is zero. Okay, so that's it. So any questions?
Can I go back to the electric field? Electric potential.
Good.
Yeah, so the white line there in the
Yes.
middle of the circle is zero.
No, if you see into this color bar, you are in this position.
That's no, that's not zero, right?
No, that's not there.
Purple is zero.
Oh, purple is
Purple is zero.
Oh, okay, okay. that
Okay.
makes sense, okay.
So that's the electric.
Can you just explain one more time why the center of the conductor has electric? It's
Yeah, so the point is that I asked the professor that why I'm looking these electric line streamlines are inside it. So he said that the streamlines are not important here. It's the electric field, right? So if we go into the arrows to see the arrows, right? So then we will be more clear. So let's suppose disable and then go with surface arrow surface. Okay, so plot, you can see now. Now you are clear with this, the electric fields. Okay, so these were the streamlines option that was not correct in a way. But when I tried the other domain, the terminal domain, it was not there. But for the streamlines, this comes in. But if you go to the arrow surface, you can see the electric fields which are not in the conductor, right? So this is the arrow surface option.
so you're saying it's because of when you energize it with a terminal?
Yeah, I think it's
Okay.
just my thinking, but because I tried with other boundary options, so it was not appeared in that.
Okay.
But I'm just going the easy way, and later we will complicate the things and go to the and like in that way. So right now you are clear the electric fields.
Yeah.
Okay, so here is the option. Here's the option. Like you can increase the number of arrows. Let's suppose if you want to increase the number of arrows to 30 or 30 here, then just hit the plot and they will be more in number. And if you want to increase the size, then you can see the size. You can increase it with this scale factor option. Yeah. Okay. So this is the you can say the monopole having a positive charges on it. And this is the basic example related to the electrostatics. Clear? So any questions online? No? Okay, so
Mike is
He's using professor.
so can you hear my voice on this your computer?
That's right. Do something.
Hello?
I can.
Yeah, so it's there. Okay, so any questions online?
No, thank you.
Okay.
Okay.
So this is the very introductory class. So we have just that I'm just giving you the little bit intro related to that, and later we will go in detail. So Professor, this is
You finished with the two things?
no, this is the first thing.
Okay.
That is the monopole, electrostatics.
Yes.
Yeah.
But
So-
get rid of the colors.
Okay. So just
Get rid of the colors and get rid of the equipotentials too.
okay.
There you go. This is put more arrows. Okay, so this is what we need to see, right? Is the lines of force, the vectors that come out of that. So along those vectors is where the force is being felt. Okay, fine.
Okay. So should we go to the next?
Go to the next one, yes.
Okay, so just for the next simulation, we have to do this in a magnetic field and the same way, 2D, and there is an option electromagnetic fields, and in that magnetic fields, it is study and then stationary. Okay, the same way we will create the geometry. And since this is the very first class, so I didn't want it to edit that case. So I'm just creating this separate case for simplicity. So for the geometry, there's the option sketch, circle, same way. Let's suppose that's the conductor size. Okay, and it's the separate one. Yeah, and that's the, now we can edit the sizes as per our wish. So let's suppose the first one is by default now 0.2 meters. So let's suppose make it millimeters. So, oops,
No,
and that's 2 millimeters.
leave it at 2.2 meters.
Yeah.
Leave it 0.2 meters. It doesn't matter. Just leave it the way it was, 0.2 meters.
It's the same. Yeah, yes, I wanted. Okay, so the point is that we can change the dimensions over here.
Put one
Okay,
instead of
one.
Yes.
Okay. Oops, and what I'm doing. Circle 1 with point 1, and that is 0.5. Right?
Okay.
Okay, so then materials, the same way we did earlier, air and copper. So that's air, that's copper, and now to the magnetic fields. Now here we have a different option. Previous we had electrostatics, but here we have magnetic field. Just right click it, and there is option coil. So just that's the coil, and then the same way we did the mesh and the study. Okay, so that is magnetic flux density norm. So if you want to see the magnetic fields,
I want to see the arrows.
arrows.
Only arrows matter.
Okay, so in this, just right click it, surface arrow, and then plot. And just disable this thing. Disable. These are the arrows.
Now put more in arrows and zooming to the conductor a little bit.
So maybe we are doubling it.
No, more than double.
More
probably
than double.
50. Yeah, all right. Now
So-
zoom into this and make them larger. There you go.
So here's the
Zoom.
option of a zoom in.
There you go. All right. So this is a beautiful field force, magnetic field force. So we know the magnetic field is concentric around the conductor, but you can see that there is field outside the conductor and inside the conductor, and it's all circular. Also, you can see that as you move into the conductor, is going to towards zero. Remember, according to Ampere's law, the field inside, it depends on the current that is enclosed. The current enclosed in the center is zero, so the field is zero. But just a little bit outside, we will find a field. The maximum field will occur at the surface of the conductor, and then it will start decaying. Give me the cut, please.
Okay. So for the in the data set, there is option cut line 2D and plot, right? And now over here, I click, no, yeah, 1D plot group, non-graph, and okay, there it is.
So this is the magnitude of the magnetic flux density. Starts at 0. At the center of the conductors, it starts at 0 and raises linearly up to the maximum point at the radius, and then it decays exponentially. It's not exponentially, it would be a log decay. As outside the conductor. So this is the typical figure that we will show or we will see. So some magnetic field inside, nothing in the center, maximum at the surface, and then it decays outside in the air. Okay. The question that I asked before is, why is it not 0 at the end? Why is it still has a value, about 410 to the -7. It's a small value, but it's about, I would say, 20% or so, 10%, 20% of the maximum. Why is it not 0?
No returning correct.
Yeah, because we are violating Ampere's law, right? We are violating, no Ampere's law, we are violating continuity. We didn't put anywhere the current coming back. So if you were to compute the energy stored in the whole thing, it will be infinity. So the current needs to come back somewhere. At that point, then you keep on integrating current, and at that point is 0. Since we didn't do it, the magnetic field is not going to decay to 0. We put only one current, right? We shouldn't put only one current, never, because the current needs to come back somewhere. You're violating the continuity of current, right?
But if you increase that length to infinity, it will come to 0 at some point.
It will never come to 0.
Almost 0. Or
It's
some
an
some
exponential e to the negative
yeah.
something.
Yeah.
It will never be 0.
Yeah.
And if you were to integrate the energy will give you infinity. So, and this reason is because you're violating the continuity of current. You are injecting current without coming back in the model. So it needs to come back somewhere. So otherwise, you are not solving a physical problem. This is a typical illustration, but at some in the reality, in the physical reality, the current needs to come back somewhere. Yeah. Yes or no? You're not clear. Current needs to be continuous.
Yes.
Here is not continuous.
Mhm.
Yeah. So we are violating this.
Mhm.
Yes, question.
The peak point of the graph.
Yeah.
So is it dependent on the potential we apply, or
It depends on the current.
So
Is the current enclosed? So the peak is computed H dot the L, let's say, equals to the current enclosed. So whatever is the current enclosed will give you, when you enclose the maximum current, will give you the peak. The maximum you enclose here is at the surface of the conductor.
Professor De Leon, maybe you can do the simulation considering the boundary as a coil
Yes,
with the
yes, yes.
surface coil with the current
Yes,
in the opposite direction.
we
and see
can
that.
do that, certainly. Yes, that's what we would do. But the example is a little bit also to make sure that you need to account for things, physical things that it may not be so obvious at the beginning. But indeed, the way is we have a return current at the boundary. Or better still, if this is a concentric conductor, we will have a concentric wire or concentric surface where the current comes back. But this is just a little example for now. Yes.
Why the raise?
It's
the
linear.
increase is very steep and
It's linear. The increase is linear,
but the drop is very.
but the drop is not, because it all depends on how you're integrating this. You start with 0, the current is 0, right? So the field is 0. You integrate a little bit, so let's say you have this is your conductor. Here, nothing. Here, you have this current. Here, you have that current. Over here, you have the total current. And then once that you get there, it goes out because it's not enclosing any more current. This term remains constant. You know, and this will change. This will be, let's say, if I were to integrate, it would be 2 pi r h. So it will be enclosed by 2 pi r. So it's a hyperbola. It's not really an exponential, or it's a hyperbola. It's 1 by r. Yes.
In this way, why would it be linearly increased? Because if we are having an
It's
uniform
Uniform distribution.
distribution and
Yeah.
current density.
Yeah.
So if you increase the diameter, it will be increased by r squared. So it should not be a linear, it should be,
Perfectly linear. You will see when you do the integral, you will see that you have an r. In the cylindrical coordinate, you have an r. So that drops your r squared to only r. Yeah. Yeah. Okay. Thank you, Fayaz. So stop your thing and we come back to where we were. So share. I'm going to share again. Please, if there are any questions, just interrupt me, right? It's we were going into this divergence. Okay, so, and we have somehow developed the tool. So the divergence is that thing in orange there that we're going to do. Now, how are we going to compute it? That is the how do we compute divergence? And this is the beautiful thing of this, I would say, not quite formal mathematics that I'm going to do, but it's very good. For example, I'm going to copy this figure here, copy, put it back here. So what I'm going to do is to do the integral of a point by point, right? Or say surface by surface. And let me take this face, the face that is facing me. And of course, I want to go to the center of the point. I want to see eventually collapse it to the center. But I need to do the integral of that surface. Integral, let me call it area 1. Integral of area 1 of the field, which maybe let's call it F. And in this case, the field coming out is only Fx, is the component X. The field is, let me put a space here. Not there. So the field vector will be given, as we have seen, it will be a function of X, of Y, of Z. Let's not put it a function of T. And it will have 3 components, Fx, which is Fx of Y of Z in the direction X, plus Fy of X of Y and Z in the direction Y, and F of Z, X, Y, and Z in direction Z. Now, the the part of the field that goes perpendicular to here doesn't account for any flux in that surface. So I don't need to put it. I only need to put the fx because this is the x direction. So for the first integral, for area one integral will be f of x, which is a function of x, of y, and z. And the derivative, the surface derivative, which will be dy dz, right? That would be the way that I would integrate to compute. The idea for now is to compute the flux that is coming out through this face of that rectangle. Okay, but yes, this is the most important thing. Don't get distracted. You're paying attention there?
Yeah.
Oh, very good. This is the central part of the course. Understanding this, Maxwell equations are nothing. Okay, so let's do then, let's see what are the coordinates of these points, right? The coordinates of these points. The coordinate of that point over here will be x plus delta x by 2, because this measures delta x, right? This is the delta x, so it's pushed forward delta x by 2. And let me actually put it farther. The coordinate of that point is x plus delta x by 2, comma, y minus delta y by 2, because it's delta y behind, and comma z plus delta z by 2. That is the coordinate of that point. The coordinate of this point, right? It will be, well, it's very similar. The only thing that changes is the y, right? So it will be x plus delta x by 2, comma, the y is different because it now is not negative, now it's positive. It will be y plus delta y by 2, and the other remains the same, which will be z plus delta z by 2. All right. Now let's do the other points. This point over here. This point over here will be delta plus delta x plus delta x plus 2. It will be the same y positive here, y plus delta y by 2. But now the z is negative. Is z minus delta z by 2. And the last one is this point. This one will be x plus delta x by 2, comma, y minus delta y by 2, and the positive z plus delta z by 2. And those are the limits of the integrations that I have to do. I have to do 2 integrations, right? Or, yeah, 2 integrations I need to do for only the flux that comes through phase A. If I want to compute all the flux, I need to do the same for all other sides. But let me do only one side to start. Yeah. So, yes.
Why did you take negative sign on y?
Which negative sign of y where?
The left one, upper left,
Here?
the upper one, yeah. Both.
This one?
Yeah.
Because the point is here, right? So you are in y behind. This point over here is the center. Let's say the coordinate of this point. The coordinate of this point will be x, y, and z. And it's in the center of the cube. So if you move in the y direction towards the negative side, it will have to be minus that, right? Okay. So I am just going to do the first one, right? So x doesn't change. If you see x is the same, x is the same, x is the same, x is the same. in any case, I am not going to integrate with respect to x because I need to measure the flux and I need to integrate in y and z. So this integration has two integrals. Let me actually, yes.
Minus.
Which one should be minus?
Lower corner, left corner.
The lower left corner should be minus where?
Minus.
See, yes. That should be minus. Thank you, Sijas. The only one not sleeping. Yeah. Everyone else is sleeping or just believe in me. Don't believe me. I can tell lies. Oof, I can tell big lies. You don't believe me? I can tell big lies. I'm going to show you a big lie that I can tell. Let me see. Rudy. I'm going to tell you the biggest lie you can imagine. Where is it? Here. Open. I have invented the device that is going to solve the energy problems of the world. It's called the turbo encarbulator. And that solves every problem related to electrical energy. Yeah. You see how big lie I'm telling? So this is just a big lie. This doesn't exist. It's just a joke. But if a professor says with authority, you try to believe it, right? So don't believe everything. In fact, don't believe me anything. Just check it yourself, everything. Okay, and this is recorded, so it doesn't exist, but it is a monster device that solves all the energy problems of the world. Anyways, what's that? It doesn't. The explanation is there. You want to see the explanation? But it's I'll show it to you later. It's just a big joke. Yeah. Okay, so we need to do this integral. I am going to somehow reduce it a bit to the left. I need to push it to the left and like that. All right. We need to do this integral. This integral will have two integrations, right? It's going to be from z equals to minus delta c by 2 to c to plus delta c by 2. And it's going to go from y minus delta y by 2 to y plus delta y by 2. And the function is only the function of x, but the function of x is going to be evaluated at the face right here, right? I am going to evaluate the function at the face because that's where I need to do it. So it's going to be f of x plus delta x by 2 so that it comes to the face, and then y and z are the variables, and dy dz. And I'm going to say that this integral is about the same of f of x. Let me see. I'm going to here. This is approximately equals to f of x at x plus delta x by 2, comma, y and z that multiplies for area 1. Of course, area 1 will be delta z times delta y, right? Whatever that is. So what I'm trying to say is I am going to keep this value constant because remember, I don't want to do integrals. I really don't want to. All integrals have to have a constant value. And because I am going to take the limit when delta x and delta x goes to 0, So in any case, I don't need to integrate anything, right? It's going to be just a point. All right, so that is the value on this phase. What would be what would happen to the other phase? Let's say the phase behind. Now I'm talking about this phase, the one phase that is hidden that I don't see, but is underneath, right? The far face. So not the front face, the far face. I can go again and look at the coordinates of these things, at the coordinates of that thing, and do the integral again. And what I'm going to get really is that the integral over area 2, which I'm going to call it area 2, the integral over area 2.
I think that's mine.
You are the one who is sharing. Yeah, yeah.
So, not really.
No, okay,
It's working fine.
it's working fine. So what happens is that I move this guy a little bit. All right, like this. So when I go to the integral of, it will be f of x, the integral will be x minus delta y, delta x by 2, right? And it will have x and y. Now y and z, it will be, now is the negative, because remember the direction of areas, the direction of area is coming outwards the volume. So this one is positive x, and the direction of this area over there is negative x, right? So it will be the negative of the same integral, right? It's the same thing, but now with different limits. Minus delta z by 2, z plus delta z by 2, and then the y minus delta y by 2 to y plus delta y by 2. And the function is the same, f of x minus delta x by 2. That's the only change, y and z, dy dz. And this is approximately equals to f of x minus delta x by 2, comma y, comma z. All right. Now, if I were to do, let me then, do the entire thing. If I were to do the entire thing, which means I repeat all that for this rectangle and that rectangle, and then go again and do it for a this other rectangle over here or square, I will get this. I will get that the closed integral of f dA and divided, let me do it right away, by delta V will be the first thing I got here, right? This term here, which I'm gonna copy. I am gonna put it here. It will be paste over there. So it's gonna be this one minus this other guy over here. Copy. Paste, put it there. Let me delete this thing, right? And let me move it a bit far closer to here. So get the blue minus that, and it will be divided by delta x, delta y, delta c, and this is, well, multiplied the whole thing by delta x, delta y, right? Delta y, delta z.
A inside.
delta y, delta z.
There needs to be another A1.
No.
inside.
No, this one goes. Yes, no, this is the area. This is delta y, delta z, like that. The area is here. This is A1, which equals to A2. Okay? And this is the volume. Okay, now I have, I can develop the all others, which I would recommend that you do them in yourselves, but it will be like this, right? The next ones will be f of y of x and y delta, no, x and y plus delta y by 2, comma z, minus fy of x and y minus delta y by 2, comma z. And this will be multiplied by delta x, delta z, divided by delta x, delta y, delta z. So of course we can eliminate as many things there. Then just for completeness, I will put the other one. We will be fz of x, y, and z plus delta z by 2 minus fz, x and y, and z minus delta z by 2. And it will be, delta z will be delta x, delta y divided by delta x, delta y, delta z. Now, I can eliminate a lot of things. I can eliminate these two things with these two things. I can eliminate these two things with that, and I can eliminate that with these two. Okay. So I can, and then I am going to take the limit. Let me take now the limit, because out of this, I need to take now to define the divergence of this vector f. I need to take the limit when delta volume tends to 0 of the integral, closed integral of f dot dA, right? And divide the whole thing by the volume. 1 by delta v, the integral of f dot dA, right? That's what I need to do. And I have all this integral already divided by delta v in there, but the limit, I have to take delta x tends to 0, delta y tends to 0, delta z tends to 0. So how it is if you look at this, let's look at the first term. Let me put it in black, in blue. The first term will be f of x, x plus delta x by 2, comma y, comma z, minus f of x, x minus delta x by 2, comma y, comma z, divided by delta x. That is, I still need to take the limit of this, right? This is the integral over here. So here is this part. I'm talking about this is this part. Let me put it in this color. Here is that. Then the second term will be f of y, x, comma, y plus delta y by 2, comma, z, minus fy, x, y minus delta y by 2, comma, z, divided by delta y. And the last one, these are some adding. And the last one is fz, x and y, comma, c plus delta z by 2, minus fc, x and y, comma, c minus delta z by 2, and divided by delta z. And when you take the limit, you will know that the divergence of f will be the partial derivative with respect to x of fx plus the partial derivative with respect to y, with respect of the y, plus the partial derivative with respect to z of fz. Holy smokes. What does this mean? Well, this is the greatest thing you can imagine because it means that the tool that we have decided, which was this tool over here that can measure, this measures flux produced at a point. That's what this thing measures. But that integral is impossible to do. But I don't need to do the integral. I need to take the derivative. This is easy to compute. So this is a great progress. So I have to, instead of looking at Maxwell equations as this crazy thing over here, right? I can use, instead of surface integrals, I can use derivatives to compute it. So that is the I would say the magic of all these things, that rather than doing the integral, I can take derivatives, and derivatives I can always take. Not only that, differential equations I can always solve. So, and that's what finite elements is going to do. So then, of course, this applied to a point. This is easy to compute, and this is the same meaning. So divergence of f, which we have defined as the limit when the volume tends to zero of the integral, closed integral of f dot the area divided by the volume, can be computed that way. So the only thing that I can say is, wow, how easy you made it. Hey, you need to go through all this math, right? But somebody made it so easy. Just look at the book at Che. It goes this way. It derives all these things exactly the way I did. Yeah, I copied from Che. Yeah. So, a tool that comes from a very difficult mathematical tool, which is a surface integral of a closed surface integral, can be made easy by taking derivatives. Okay. All right.
I have a
Question, yes.
So the math looks very smooth.
Yeah, it's very simple. It's just calculus, not even calculus, because I don't do any integral.
Yes.
Everything is constant.
So at the very beginning, when you do area A1,
Yeah,
uh,
here.
go down a little bit. Oh, yeah, yeah. When you see, yeah. So when you see that, you said that you cheat a little bit to make fx to be constant.
Yes,
But when it comes to a very small area, it's not.
it's not,
at all.
it's not cheating at all, but it's not a mathematical. I'm not using the chain rule to get these derivatives and these things, right? I am just making it small, approximately. The only thing you have to really do is, instead of working with derivatives, you work with increments, right? I'm not working with the definition of derivative at the very end. Yeah. So I'm doing this integral. I'm considering the step that is not absolutely mathematically correct is, this is a function, right? And I am saying that value is constant. And then I don't need to do the integration as such. I just the integration becomes a multiplication by delta y and delta z. That's what it means. That I am considering these things constant. Yeah. That's all it means. And this thing is taken out to the surface. So it's not in the center, right? It is. Let me see if I can extract it again. Come on. What is happening for us?
Lower left. Okay.
Yeah, it doesn't work. Let me see. Insert page above. All right. So the only trick is that I move this point or move this point. Come on. Move this point to the center of this face. Right? Move this point, and this is delta x by 2. Instead of saying x, y, and z, which that would be that point, the point on the face will be x plus delta x by 2, comma y, comma z. Right? And then take the limit to the point. But at the beginning, just push it out so that it comes to the surface and I don't need to integrate anything. That's all what I've been doing, is trying to cheat a little bit with the manipulation such that I don't need to do any integral, because integrals are difficult to do. And I don't know. How do you do the integral of something? You go to a table.
I just hope we could free
Yeah.
the tables.
You go to the table, right? Or, well, today we don't even go to the table. We just ask ChatGPT, give me the integral or something, and it gives it to you. But those integrals of very complicated functions are impossible to compute. There is one exception. Have you ever seen those big books of Russian integrals, compendiums and compendiums of integrals? Have you seen them? No. Well, I have a couple of them, but there are many Russian books with hundreds or even thousands of integrals. And those are because some mathematicians were put in the gulags and they were forced to solve the integral to buy their freedom. Of course, it's a joke. Don't believe me. Yeah. But I think that's the only way. You buy your freedom by solving this integral. Otherwise, why would anybody have the time or the motivation to do an integral that is going to take, I don't know, 100 pages to solve? Yeah. No, it has to be mathematicians in the gulag. It's the only explanation I get. It's of course a joke. Yeah. So any questions down in Mexico?
No, thank you.
No.
Okay, so I will post the notes. I will even try to get now I have Carlos here with me. I'm gonna try to create a web page for the course and publish these things for you. If not, I will send you the same thing as did before, give you permission to access the recordings if you want them, even though I know that Fermin has already stole the video. Very good, Fermin.
Yes, Dr.
Yeah.
Francisco.
Okay, so